Okay, so I'm carrying on working through Colin McCarthy's elementary categories, elementary toposes, and I'm going to do some of the solutions to some sort of selected exercises from the end of chapter 2. So, first one, exercise 2.1, we're supposing that we have a product P of A and B with projections P1 and P2, and then we're supposing that there's a non-identity isomorphism I from P to P, so kind of non-identity automorphism, if you like, and we're asked to then show that there are projections other than P1 and P2 from P to A and B, which are forming another product. So we just basically use theorem 2.1. Let me just restate theorem 2.1. If P, P1, P2 is a product diagram for A and B, and there's an isomorphism F from Q to P, then Q with projections P1 after F and P2 after F is a product diagram for A and B. So we basically just use that directly with, so if we just take P again as our object for our product and we use Q equals P1, Q1 equals P1 and Q2 equals, so if we use Q1 equals P1 after I and Q2 equals P2 after I, then we have these other projections from P which are forming a product of A and B, and of course Q1's not going to be equal to P1 and Q2 is not going to be equal to P2 because I is not a identity isomorphism. Okay, because if these projections were equal, then we could show that I was identity. Okay, so next one, let's do exercise 2.3, and that's basically just to show a couple of equalities, particularly n times m after f times g is nf times mg, and we can see that just by sort of expanding out what these multiplications of arrows are in this sort of angle bracket notation, and just grinding it out, and we get the appropriate result. In a similar way, we're asked to show that f times 1, well, 1 is identity arrow, so f times 1 after 1 times g equals 1 times g after f times 1, and again we can get these just by sort of grinding it out by writing things in angle brackets and just keeping using this trick of pulling in this angle bracket to the right of the two things in the angle bracket to the left, and evaluating and so on. Now this is a very interesting exercise, exercise 2.5. So suppose we have a categorical product of A and B with projections P1 and P2, and so then if we have an object A, of course we have a arrow, the identity arrow of A going from A to A, and suppose we also have an arrow F from A to B. Well, then the kind of unique intermediary arrow that makes this diagram commute, we can call that gamma of F. The sort of proper notation for it is 1A comma F, and that's called the graph of F. And it's a wonderful name because if you think about what it does, so think about a graph as in a plot. So if we think about A and B as the set of real numbers, let's say, what this is doing is it takes in a value of A, and then it sends it to the kind of pair. So what we have is, for example, that gamma f of little a is a comma f of a, and that's nothing more than the coordinates of that point on the graph. So this is literally sending sort of elements of A to sort of points in this sort of product of A and B. Elements of this product of A and B. Now, also notice that this is really a subset of A times B. In this picture here, it's like a one-dimensional kind of subset of this two-dimensional plane here, this curve. So it should correspond to a monomorphism from A to A times B. And in fact, the exercise is to show how we can construct gamma f, or how we can consider gamma f to be an equalizer. And indeed, every equalizer is a monomorphism, a monic. So it all makes sense. So what we're asked to do in this exercise is to show that gamma f is the equalizer of f after p1 and p2. So we can do this because, I mean, instead of writing gamma f, let's just write its proper name, which is 1a comma f. So f after p1 after 1 comma a comma f is just going to be f, and also p2 after 1 comma a comma f is just f. So yes, gamma f does equalize fp1 and p2. Now let's suppose that h also equalizes fp1 and p2. Well, we can write h as alpha comma beta, because it's an arrow from t to a times b. And then this sort of equalization condition means that we have to have that p2 of h, which is beta, has to equal fp1 of h, which is f of alpha. So we can write h is equal to alpha comma f of alpha, which is 1a comma f after alpha. So we have h is 1 comma f after alpha. So we have that there is this alpha such that the graph after alpha is h. But we need this alpha to be unique, so let's get that. So let's suppose now that h, which we know is alpha comma f of alpha, is equal to 1a comma f after gamma. So we're going to assume that this intermediary arrow is called gamma now. And then since these two things are equal, we need them to be equal on components, so we need gamma equals f. So yes, this intermediary arrow is unique and this thing is an equalizer. The second thing, another important notion, is the idea of a diagonal. So the diagonal delta a is just 1a comma 1a, and we're asked to show that h times k after the diagonal is h comma k, and we just get that by sort of writing things in the angle bracket notation and calculating it out. Okay, exercise 2.6. Suppose that we have an isomorphism h from A to B and an isomorphism k from C to D, and we have an arrow f from A to C and an arrow g from B to D. Well, we have to show this equation that f h to the minus 1 equals k h to the minus 1 follows as a consequence from this equation here, which is Kf equals GH. And so all we do is just get this equation and then compose it with a k to the minus 1 on the left and h to the minus 1 on the right. And, you know, the inverses cancel out and we get this formula. There's a few exercises to do with duality. So basically you get the dual of an argument by reversing the directions of the arrows, and lots of interesting things happen when you do that. So I've made this sort of table. So if you have an arrow f from A to B, the dual notion is an arrow f from B to A. The dual notion of a domain of f is the codomain of f. When you dualize, identity arrows just become identity arrows. Equalities stay the same, but we have to reverse the order of composition. So if in the original category we've got G after F, when we dualize, the arrows reverse and this composition becomes F after G. Isomorphism is a self-dual concept. So the dual of an isomorphism is an isomorphism. Dual of an epic is a monic. Dual of a split monic is a split epic. If you look at the basic axioms of category theory, axioms 1, 2, and 3, they are self-dual, so they just become axioms 1, 2, and 3 again. And that means that basically we can do this dualization because the fundamental axioms that we're building on are self-dual, so we can always dualize the consequences that we prove from those axioms. Now, if we're assuming other axioms, they may not be self-dual. So, for example, if we're, say, working in a category where we're assuming that there are always limits, but we're not assuming that there are always co-limits, then we can't just automatically dualize any of the consequences we get from those assumptions, because then the axioms wouldn't all be self-dual. Anyway, the dual notion of a product is a co-product. The dual notion of an equalizer is a co-equalizer. But basically the idea is that if you do these kind of substitutions, replacing domains with codomains and reversing composition and so on, you can always dualize results as long as they're just based on the basic axioms of category theory, axioms 1, 2, and 3. This is an interesting exercise. So exercise 210, suppose we have an equalizer E of f and g. We're asked to show that these three statements are equivalent, that E is epic, that f equals g, and that E is iso. So let's do this. Suppose f equals g. Well then, taking E to be the identity of A does indeed form an equalizer. And so then we know that any equalizer E dash of f and g, basically for any such equalizer, we have that there exists a unique V such that EV equals E dash, and since E equals the identity arrow of A, we have E equals A, and we get that E dash equals V, so V is just a isomorphism, and such an isomorphism is going to be, so E dash equals V is just a isomorphism, and we know such isomorphisms are epic, and of course they're isomorphisms. So we've shown that this middle statement implies a statement on the top and a statement on the bottom. Now let's suppose that E is iso. Well, then he's obviously epic. And suppose E is epic. Well, then we know that E equalizes f and g. So fe equals ge. But since E is epic, that implies f equals g. So that proves this result. Now 211, we're asked to suppose that any split, we're asked to show that any split monic, E from capital E to A, which has a left inverse h, is an equalizer of identity of A and E after H. So we can do this because one A after E equals E. Equals E after 1E. And we have the H E equals 1E. So we have E1E equals EHE. So that shows that E equalizes 1A and EH. Now suppose that K also equalizes them, so we have EHK equals 1AK. Well then, if we just take U is equal to HK, then we get that EU equals K. So such a U will do as an intermediary arrow. But now let's suppose we have a different one, or we have another one. So we have that EV equals K. Well then, if we just use our left inverse, we get that HEV equals HK, and HEV is just equal to E because we're using this left inverse H. So that shows that the intermediary arrow is unique, because this V has to be equal to U, so E is a equalizer. And I'm not doing this other exercise, but it does introduce some new terminology, so I'll just mention the new terminology. We say an object P is a subterminator if there's at most one arrow to P from any object. Okay, so it's like a terminal object, but we don't require there to be exactly one arrow from any object, just at most one arrow. Okay, that's going through those exercises.